Welcome back to our course Measure Theory for Probabilists. We have defined the integral with respect to some measure. We have obtained important convergence result last time, dominated convergence, monotone convergence, and the lemma of Fatou, and that's something we will need today. Today we are going to introduce so-called LP spaces, which are classes of functions or sets of functions such that this function f, for this function f to the power of p is integrable. So let's start. So what are LP spaces to start with? Here we have the definition. So p is some number bigger than 0, can also be infinity. Let's see what that means in a moment. And as I just said, f needs to be not only integrable, but f to the power of p needs to be integrable, which means this here. So f to the power of p, which doesn't always make sense, though we have the absolute value of f to the power of p. This here needs to be integrable, which means, okay, this what we will see is a norm. This norm here is finite, which only means that mu, so this here is the case, if and only if mu integral f to the power of p is finite. Because the number is finite if and only if x to the 1 over p is finite. Okay, and that's for p smaller than infinity, and for p equals infinity, we have this thing here. So there is a number k such that f is not bigger than k almost surely. So f smaller or equal to k equals the whole space. So it equals mu of the whole space. So if that's the case, then k here, the smallest number, is the infinity norm. So one also says that's the essential supremum. It's not the supremum because f could be greater than k, but only on a set which has measure 0. So it's almost everywhere smaller or equal than k. Then k is the infinity norm of f. Okay. Well, I said f that's here is a norm, and you can easily check that. Well, not really. We'll be able to check that in a moment. So one thing is easy to check. So the norm of a times f, where a is some real number, that's the same as the absolute value of a times the norm of f. That's something very easy. When you plug that in here and use that, you can pull out the a from the integral. Another thing which you will need for this double bars to be a norm is, the triangle inequality. So that's this thing here. We will prove that on the next slide apparently, and this here is called Minkowski's inequality. Here in a version for p bigger or equal than 1. There are also versions for p smaller than 1, but that's rarely used, so we don't prove that here. And in order to prove the triangle inequality here, we need the so-called Hölder's inequality. And that's the following. While the triangle inequality deals with the sum of two functions, Hölder's inequality deals with the product of two functions. And here we have a funny relationship, 1 over p plus 1 over q equals 1 over r. Here's the r on the one side, and p and q are on the other side here. And then Hölder's inequality claims that this inequality here holds. Let's try to prove this. So first, if p equals infinity, or if the norm of f is 0, or if that's infinity, or if the norm of g is 0 or infinity. All this here is clear. For example, if this here holds, that means f is 0 almost everywhere. If f is 0 almost everywhere, then here we have a 0. But then also f times g is 0 everywhere, because we have a product of f and something, and that's 0 if f is 0. If the right hand side is infinity, okay, there's not much you can do, because then the inequality just holds. And the last thing is, if p equals infinity, then this here is the essential supremum. And you basically know that you can pull out f here, and then you have the inequality also. So we can assume that no case like this here occurs. So that's here okay. Otherwise, we take an f tilde and a g tilde, which is f divided by the p norm of f, and g tilde is g divided by the q norm of g. And when we set this here, we just have to show that the r norm of f tilde times g tilde is smaller or equal to 1. Because this here, well, when you plug in f tilde and g tilde here, you can pull out 1 over p norm of f and 1 over q norm of g. Sorry, here's a typo. Like this here, to the other side, and then we exactly have the inequality here. So that's what we have to show. We have to show this here. Then there's one inequality which deals with the convexity of the exponential function. So recall what convexity means, and let's just use here the exponential function. Convexity means if you take a point here and a point here, and you make the connection here, and that was not a good draw, like this here, let's say, and you take some intermediate point between these two here, then the function itself is below the line which connects this point and this point. So that's convexity in a picture. And what does convexity mean as a function? That means if you have here some value, let's call it a, or yeah, a like here, b like here, then this here. So in the middle we have, let's call this gamma times a plus 1 minus gamma times b. So this here is a combination between a and b. A is weighted with gamma and b is weighted with 1 minus gamma. If gamma is 0, we are at b. If gamma is 1, we are at a. And if gamma goes between 0 and 1, we are somewhere in between here. So if gamma goes from 0 to 1, we are somewhere in between here. And a function is called convex if the function value at this point here is below the line. And what's the value of the line? Well, that's gamma f of a plus 1 minus gamma f of b. So this here is convexity. And as you know, the exponential function is convex, which we can use in order to write x times y to the power of r. Well, let's first introduce the exponential function. e to the power of r over p times p log x, brackets here, plus r over q times q log y. And important point, r over p is the gamma here. So r over p plus r over q, which is then here gamma plus 1 minus gamma, that must be 1. And actually r over p plus r over q, when you look at this here and multiply this equation here by r, you have r over p plus r over q equals 1. So the sum of these two here, that is 1. And here is one value, and here's the other value. So let me just write. So that's the gamma here, that's the a, that's the 1 minus gamma, and, oops, sorry, that was no a. So that was the a, and that was the b. And convexity means this here is smaller or equal than gamma, that's r over p, f of a, e to the power of p log x. And when you recall the rules for exponential functions, that's x to the power of p. And the same on the second part, r over q times y to the power of, q, like this here. So that holds. And now we have to prove this inequality here. And, well, I can also put a power of r here, because that has the only fixed point 1. So f tilde g tilde r norm to the power of r, which is, by definition, well, if you have this here to the power of p, I'm sorry, if you have this to the power of p, you just don't have this here. So that's mu f tilde g tilde to the power of r. And this here, now we can use the inequality here. F g to the power of r is more or equal than r over p mu f tilde to the power of p plus r over q integral of g tilde to the power of q. Yeah, and the right hand side is 1 because, well, this here is 1 by definition. So this here to the power of p. I have f to the power of p, and here the integral over f to the power of p. When I integrate that, I have 1. So this here is 1. This here is 1. And r over p plus r over q, we had that is 1 also. So we're done because we showed this. Okay, now that was the first very important inequality, Hölder's inequality, which we'll need also more often, I guess, at least in the next lecture on probability theory. Then we are ready to prove the triangle inequality, which in this case is also called Minkowski's inequality. Again, something is clear. So if p equals 1 or infinity, the thing to show here is clear. So if p equals 1, that's just the usual triangle inequality here, because we have mu of, so integral of absolute value of f plus g is more or equal than absolute value of f plus x plus absolute value of g, and that's just the usual triangle inequality for the absolute value. for infinity, well, basically the supremum of sum is more equal than the sum of the suprema. So let's use p is bigger than 1 and smaller than infinity. And in this case, we set q to be p divided by p minus 1. And r, well, as 1 over p plus 1 over q. And what is 1 over p plus 1 over q? That's 1 over p plus, okay, 1 over q is p minus 1 over p. And 1 plus p minus 1 is p, and p divided by p is 1. So r is 1. And apparently, well, this then is of course also 1 over r if r is 1. So we have 1 over r is 1 over p plus 1 over q, which means we can use Hölder's inequality here for this r and p and q. And we do this and write the p norm to the power of p of f plus g. So here what we have is mu integral f plus g to the power of p. And apparently I have p powers here. I can split off one of them. So f plus g times f plus g to the power of p minus 1. And the first one here I split the f plus g to the power of p minus 1 plus mu g times f plus g to the power of p minus 1. Here I use the usual triangle inequality for the absolute value. And now, what do I have here? Well, what do I have here? And now I want to use Hölder's inequality. I have a p minus 1 here. And let's just assume for a moment that I would have a 1 over p minus 1 here. Then I would have here the p minus 1 norm of this thing here. But on this side here, well, let's look at the Hölder inequality. At the side of the product, I need the r norm, and r was 1. So r was 1 here. And, okay, like this here. I don't need this. I have the 1 norm of the product, and Hölder tells me that's smaller or equal than f norm, p norm of this thing here times q norm of this here. Well, I have the p norm of f times the q norm of f plus g to the p minus 1. F plus g to the p minus 1 and the q norm. And for the g, I get the same thing. I have the, not exactly the same thing. Here I do have the same thing. The p norm of g times the q norm of f plus g to the power of p minus 1. And now let's look at this here. What is this? Well, let's write that out. That's Yeah, well, the point is I have a p minus 1 here and I need the q norm, so I have to take the p minus 1, this function here, to the power of q, so I multiply p minus 1 and q, and that is exactly p. So this here is mu f plus g to the power of p. Yes. And outside for the q norm, I have p minus 1 divided by p. And I could also write it like this. So here I have a p, I have the same p, and this here I have to the power of p minus 1. And with this p and this p here, I have the p norm of f plus g. So that's mu f plus g to the power of p, 1 over p, and the whole thing here to the power of p minus 1. And this is the p norm of f plus g to the power of p minus 1, like this here. This is this term here and the same here. And I can write further fp plus gp. And down here I have the p norm of f plus g to the power of p minus 1. And now I can divide by this factor here. And what stays is just the f plus g norm, the p norm of f plus g. On this side here and here I have the sum. And that's exactly the inequality we wanted to prove. Okay. Some more things on these LP spaces. So now we have basically proved that these LP spaces are normed spaces. Just one remark, which I also write in the manuscript. That's not completely true because, well, what does the p norm of f equals 0 mean? It means that not f equals 0, but f equals 0 almost everywhere. So it's not really a norm. You have to make some quotient in order to make it a real norm space. But still, it's almost a norm. So some properties. Essentially, we have 3 properties today. First, so I write here, some map is decreasing, which means exactly this here. So I have an R in a Q, and for the bigger Q here, the space is smaller. So if Q is bigger, then I have fewer functions in this space. But that only works if mu is finite, that's important. And yeah, R has to be bigger than 1. Apparently, mu finite is necessary here. If mu is infinite, for example, mu is the Lebesgue measure, so lambda Lebesgue measure, you can have something like this function here. Well, let's draw it real quick. Here's 1, and here it falls like 1 over x. Then you have, when you square this function, you have 1 over x squared, and you know you can integrate it. 1 over x squared is integrable. But if you do not square it, you have 1 over x, it's not integrable. So this f here is in L2, but it's not in L1, which is exactly the opposite of here. So if q is bigger, so that would be the 2 here, and r would be the 1 here. So as we see here by this counterexample, L2 is not smaller than L1. There are functions in L2 which are not in L1. But as we just prove in a second, if mu is finite, this inclusion here holds. Okay, first, again, some clear case. If q equal infinity, everything is clear. Yeah, because if q is infinity, then a function in this space here has a finite essential supremum, which means I can even bound what this function to the power of r is, and this essentially in particular finite. So that's clear. Then, if that's not the case, if q is smaller than infinity, I take the R norm of f. And I have that the Q norm of f, take f in LQ of mu. So I have to start like this. So I take an f in this here, and I have to prove that f is also in this set. So f is in LQ. And R is a bigger number than Q, which means I can have something like 1 over P equals 1 over R minus 1 over Q, which is bigger than 0. Let's look at this. So Q is bigger, so 1 over Q is smaller than 1 over R. So this here is a positive number. And since this is a positive number, I find a P such that 1 over P is bigger than 0. And now we use Hölder's inequality. So this norm I can also write as the R norm of 1 times f, just multiplying by 1. Okay, that was easy. Now I have a product. I can use Hölder's inequality and take the P norm of 1 times the Q norm of f. And here I have the P norm of 1. And the norm of 1, that's just this here. So I integrate mu, so I integrate the function 1 over mu. That's finite in this case because mu is finite. So this here means exactly that mu is finite. So this is finite. And this here is finite by assumption. So this is also finite, and we are done with this proof. Okay. Next thing, convergence. So every norm, you might recall this also, defines a convergence. And that's also true here. And I just say a sequence converges to a limit if the norms converge to 0. And then we write this here. So we will have several notions of convergence of functions. Fn converges in LP to f. And a very simple consequence of our last result is if I have convergence in LQ and Q is bigger than R and mu is finite, then I also have the LR convergence. And the proof is very simple. So the R norm of the difference is smaller or equal than the Q norm of the difference. So if this here goes to 0, this here also has to go to 0 because all numbers are not negative. A more interesting feature is that these normed spaces are complete. So in normed spaces, okay, norms define metrics, and metrics, they can be Cauchy. And every Cauchy sequence in LP converges, as we will prove now. And yeah, in basically all cases where you want to show that some space is complete and you have a Cauchy sequence and you need to find the limit, the most important part is to find a candidate for the function f. And that's what I'm going to explain to you in this proof here. So take a sequence of epsilons summable. So they need to be summable. Then I know for all n, there are for each k, I have an nk such that for all m and n bigger than nk, I have that the norm of fm minus fn is smaller than epsilon k. So that's the Cauchy property. In particular, I can write, can sum something. So fnk plus 1 minus fnk. I can sum this over all k, and I can make the norm here. So that's the norm of a sum. And by the Minkowski inequality and some monotone convergence, we see that this here is smaller or equal than the sum of the norms. Fnk plus 1 minus fnk, sum over all k. This here is by assumption smaller or equal than the sum over k, epsilon k, which is finite. So what I have here is this here is finite, which means that this function here is almost everywhere finite. It's a sum over non-negative functions, and that means that this here converges to 0 at least. Yeah. So fn1, fn2, and so on are converging to 0 almost everywhere, which means if I plug in some value for, let's write like this, for almost every omega, this here is a Cauchy sequence. And since these are real numbers and the real numbers are complete, this here converges. So fn converges to some f pointwise, but almost everywhere. Because, well, for almost every omega, that's a Cauchy sequence, and for such omegas, we have convergence, and for all the others, we just don't care. And then we have our candidate f. So that was what I tried to explain to you when I started the proof. So we need to find a candidate for the f, and now we have it. And now we only need to apply the lemma of Fatou once. We want to have something like LP convergence, because that's what we want to prove. And this is, well, let's write it like this here. So that's the limit k to infinity f n k minus fn And the lemma of Fatou says that mu of a limit is smaller or equal than the limit of the mu's, at least the lim infs for existence. That always holds for non-negative sequences, and they are non-negative here under the integral. Fn k minus f. And Fn k minus f, the p norm, Fn k minus Fn. That's because I just pull out the limit here and use the lim inf, so that's this thing here. And this here is smaller or equal than the supremum, Fm minus Fn in the p norm, m bigger or equal to n. Yeah, the nk will, without loss of generality, be bigger than the n. So I make this bigger by using all possible fm's here. But we know, well, this here converges to 0 because that's the Cauchy property. So if n goes to infinity, this here converges to 0. And that's exactly what we wanted to prove. So we have shown that the LP spaces here, they are complete, which is a nice property, because once you know you have a Cauchy sequence, then you know there must be a limit almost everywhere. Okay, that's it for today. And next time we are going to shed more light on a special LP space, which is the L2. Okay, see you then.